The topic for the next few lectures includes environment semantics and closures. And as the first step, we are going to talk about evaluation judgment. So let's talk about evaluation judgment in this lecture. So first, why do we study another form of operator semantics called environmental semantics, and also a new notion called closures? So we would like to achieve an efficient implementation of substitution. So in the general form of substitution is E prime for x in the expression E. So this is a critical part of the operator semantics, and in order to achieve an efficient implementation of the operator semantics, we have to have an efficient implementation of this substitution operation. But naive implementation of this substitution is very inefficient. So for instance, in the naive implementation of substitution, we have to analyze the structure of this expression E. And this expression E could be very large, in which case we have to visit every part of this expression E to locate the variable x, and this can be quite expensive. And furthermore, we can be very unlucky because we spend a lot of time analyzing the structure of this expression E, only to find that this variable x is never found. In this case, the effort of analyzing this expression E is completely wasted. So there should be many ideas for improving over the naive implementation of this substitution. And that's the topic. And if we recall the two major topics that we previously discussed, the first is the Brown indexes, and the second is evaluation context. And these two ideas also deal with efficient implementation of operational semantics, efficient or elegant implementation of operational semantics. So for instance, we introduced this notion called the Brown indexes to eliminate the need for string manipulation for variables. So without the Brown indexes, we have to represent all variables x with string. And string manipulation is quite expensive in comparison with integer manipulation. So by exploiting the Brown indexes, we replace all these string operations with integer operations, which is very fast. So we achieve a more efficient implementation. And in the case of evaluation context, we systematically locate the next red x. So the question here is, in the case of evaluation context, the question is, given the expression E, how do we find the next red x efficiently and in an elegant way? And by exploiting evaluation context and also developing an abstract machine, we were able to locate this red x in a systematic way. So these are two topics deal with how do we achieve an efficient implementation of operational semantics. And similarly, all these topics are about how do we efficiently implement this substitution operation. So let's first talk about this evaluation judgment. So previously, we have this form of expressions, and we use true, false, and if then else. So let's consider this fragment of simply typed lambda calculus. And values include this lambda abstraction and true, false. So this is the syntax. So in the previous formulation of operation semantics, we use this reduction judgment. This is E reduces to E prime. This is reduction judgment. And in some sense, when this expression E reduces to another expression E prime, it takes a single small step. So this is just a single small step. And in order to produce the final value from this expression E, we have to take many such small steps. So expression E reduced to E prime, E prime reduced to E double prime, and then eventually the expression reduces to value V. So in this case, we are taking many small steps. So each reduction represents a small step we take toward the final value V. So for this reason, this reduction judgment, the operation semantics based on reduction judgment is often called small step semantics. Small step semantics. This is an alternative name to the operation semantics. For the operation semantics based on reduction judgment. So this is small step semantics where we take many small steps to produce the final value V. Now, we are going to take an opposite approach. And this time, we are going to take a single big step. We are going to take a single big step to produce value V from the expression E. So we introduce this new judgment called evaluation judgment. Evaluation judgment, we write expression E hook right arrow value V. And this symbol is called hook right arrow. Hook right arrow. And in fact, if you are familiar with this LaTeX programming, the command for this symbol is literally hook right arrow. So let me call it hook right arrow. So expression E hook right arrow value V means that expression E evaluates to value V. So we are taking a single big step to directly produce value V out of expression E. Unlike these small step semantics where we have to take many such small steps in order to produce the final value V. So we are taking many small steps here. But here we are taking just a single big step to produce the value V for the expression E. So this is the new form of judgment called evaluation judgment. And the intuition behind this evaluation judgment is very simple. The idea is, if you have E hook right arrow value V, it means expression E literally produces evaluates to value V by taking 0 or more small step reductions. So the course notes actually provides complete proof of the equivalence between this evaluation judgment and this reduction judgment. So this is the intuition behind evaluation judgment. So we introduced this new form of a judgment called evaluation judgment. So it's time to develop their inference rules. Inference rules for this evaluation judgment. And they are called evaluation rules. So evaluation rules. Evaluation rules are for this evaluation judgment, E hook right arrow value V. So first, let's think about what happened to value V under this evaluation judgment. What happened to value V? So previously, if you have value V, we produce value V by taking 0 small step reduction. So this holds. So this notation represents reflexive and also transitive closure. So it includes reflexivity, which means that something reduces to something itself. So we have this judgment. So therefore, according to the intuition behind this evaluation judgment, we may use value v here. This is true, this is provable, so we have value v here. So it turns out that for value v, we have this evaluation judgment. Notice that we don't have this reduction judgment. This doesn't hold. You cannot further reduce value v. So that's it. You cannot further reduce value v. But at the same time, notice that we have this value v, reflexive transitive reduces to the same value v. So this is okay, but this is not okay. But in the case of evaluation judgment, this value v evaluates the value v itself. So we have this judgment. So for every form of value v, we will have an evaluation rule of this form. So for instance, the first evaluation rule is going to be what is the result of evaluating this lambda? This lambda abstraction is a value, so it evaluates to itself. This is the lambda rule. So this is the first rule. And what about expression, this lambda application expression E1 applied to E2? How do we produce the final value? So you have to put the final value, final result of evaluating this lambda application. So in the premise, we have to evaluate, we have to fully evaluate the expression E1, and we also have to fully evaluate expression E2, and then perhaps we will have to perform substitution, and then keep evaluating the result. So first, we have to evaluate expression E1. So let's say expression E1 produces lambda abstraction. If expression E1 fails to produce lambda abstraction, then we are doomed. We cannot further actually evaluate the whole expression. So expression E1 is supposed to produce this lambda abstraction. And then we evaluate expression E2. By the way, we assume call by value. So we assume call by value here. And expression E2 produces a value v. Now we have obtained a lambda abstraction from the first expression and a value as the argument. So the argument E2 produces value v. Now we have a lambda abstraction and its argument. So it's time to perform substitution. So we perform substitution, which is value v for x in expression E. But this is not the final result, because in general, this is not necessarily a value. So we have to keep evaluating. We have to try to evaluate this expression as well. And if this one eventually produces value v prime, then we can deduce that the final value from this expression E1, E2 is value v prime. So this is the application rule. So notice that in the premise of this application rule, everything takes place from obtaining the lambda abstraction, obtaining the argument, and performing substitution, and evaluating the result of substitution. So inside this single inference rule, single evaluation rule, everything takes place from obtaining this lambda, argument, substitution, and then evaluating the result of substitution. That's the key difference from the previous formulation where we had to take many small steps. But this time we take just a single gigantic step to produce the value v prime right away. Now what about true? True is also value, so true produces true. So it's true. And what about false? False produces false. This is false. What about expression if E then E1 else E2? So here we have to obtain the final value of evaluating the whole expression. So first we have to figure out what kind of Boolean value this expression E produces. So let's just say expression E produces Boolean true, in which case we are going to keep evaluating expression E1. So we take the then branch, so E1. But notice that E1 is not the final result. We are not going to write E1 here. This doesn't make sense because in general, E1 is not necessarily a value. So we have to keep evaluating expression E1 as well. Let's say expression E1 produces the value V, then the conditional expression produces true, so we take the then branch, and this then branch produces value V, so we have the value V. And the other case is expression E evaluated to value false, in which case we take this else branch. So let's just say E2 produces the value V, then the whole expression produces the value V. So let's say this is if true, this is if false. So let's put together all these evaluation rules and we obtain another formulation of the operator semantics based on this evaluation judgment. And this is called big step semantics. Big step semantics. Because given a particular form of expression, we are going to take a single big step to produce the final value rather than taking many small steps. Rather than taking many small steps like this one, we take just a single big step to produce the final value. But this is what is called a big step semantics for simply typed lambda calculus. And notice that for every for each form of expression, so we have these expressions, and we have a corresponding inference rule for so in other words, we don't have several evaluation rules for this application. We have just one evaluation rule. This is the difference. As a small example, let's consider the evaluation of this expression, which is a lambda. So we have this identity function, and the argument is an identity function applied to true. So the high level structure of this expression is we have this identity function and an argument. And this argument itself is an identity function applied to true. Let's try to evaluate this expression. So first, this is something applied to something. So we have to produce a lambda abstraction from the first expression. So let's evaluate this one. This is a lambda x O dot x. And this evaluates to lambda x dot x itself. Next, we have to evaluate the argument. So let's evaluate the argument. Lambda y bool y applied to true. And this one is also a lambda application. So we first evaluated this one, lambda y bool dot y. And this one produces lambda y bool dot y. And then we have to evaluate the argument. And the argument is true. So true produces true. And next, so if we revisit this evaluation rule, first obtain lambda abstraction, and second obtain the argument, and perform the substitution, and then evaluate the result. So it's time to apply substitution. So we have this lambda abstraction and the argument, and we are going to substitute true for y, so which gives us true. The result of substitution, this is actually true for y in y. So this is the result of substitution, and then we keep evaluating it, and it returns true. So this one produces true. Now, from the first expression, we have generated this lambda, and from the second expression, we have generated the argument. Now it's time to perform substitution, because we have the third case here. It's time to perform substitution and then keep evaluating the result. So let's substitute. This lambda is the argument, so the substitution is going to be substitute true for x in expression x, which is true. Now we have to evaluate this one, but this is already value, so it is true. So we have this judgment. So the final result is true, so we write true here. So as expected, the evaluation of this expression produces value true.